Welcome everybody. Good morning, good afternoon, good evening, wherever you are in the world. This is Tim Collins once again, and it's a pleasure to welcome you to what is our last webinar of 2022. And this is entitled Life Cycle Thinking, and I'd like to sort of challenge some maybe preconceptions here. Is this a paradigm shift, or is it just plain common sense? Now, we'll go into that in more detail in a moment, but first, just a few housekeeping points. So the presentation itself will be made available to all attendees. Excuse me a moment. And so there's no need to ask that as a question. And the video of the presentation will also be put on our YouTube channel, so you'll be able to access that after the webinar itself. Furthermore, if you have any questions, we would like to ask that you pitch them via the chat function. We will have time for a number of questions towards the end, but as is normal for us, all questions pitched via the chat function will get answered, whether that's during the session today or after the session is concluded. So all questions will be responded to, so there's no worry there if your burning question doesn't get answered during the session today. So without further ado, we will now move forward. So this is our normal disclaimer that this document is protected under copyright. And if people do want to reuse it or distribute it, we kindly ask that people ask our permission first. The contents of the presentation comply with antitrust guidelines by which World Stainless is bound. So we'll start off with today's agenda. There's quite a number of topics to get through in the sort of 40 to 45 minutes I'll be speaking for. We'll start with a preamble that's a little bit provocative. I hope it's a little bit provocative, just to sort of try a bit of scene setting and lead nicely into the introduction itself. Then I'll talk a little bit about resilience before moving into really what is life cycle thinking, why should we adopt it, with an example based around life cycle costing in that section, and then moving on to sustainability modeling, which I believe is a more holistic approach to life cycle thinking before summing up at the end. So that's the structure for today's session. So firstly, in the preamble, and I love the quotes that Albert Einstein is credited for, and maybe all of us have seen some examples of this in our professional lives, that people do the same things over and over again and sometimes expect different results. Well, of course, that is pure madness. But it also begs the question, are we in fact stuck in behavioral norms because our lives are overly busy these days? So, hey, there's an interesting sort of reflection on this sort of approach. But I think in terms of setting the scene before we move into life cycle thinking, we know what we're up against as a planet today. The onset of global warming, we have political instability, we have consequences of global warming like sea level rises and extreme weather events that are accelerating all the time. And then to sort of make this a little more challenging, we have the ongoing mass urbanization. So can we afford to keep behaving as we have done in previous decades? Excuse me, I would argue that low-cost short-termist thinking has dominated our belief systems for quite a long time now, maybe 50 plus years. And that has arguably, and this is a bit controversial, dominated business compensation arrangements too, that we think short-term more than long-term. And I'm not sure that's always such a good thing. So has our alignment thinking about these things shifted away from societal to individualistic? And currently, a little under 60% of the global population are living in urban settings, and by 2050, that will have grown by more than 10% to reach almost 70%. So mass urbanization is driving some of the behaviors we see, I think, but they're not all good behaviors. But let's take a step back in time, and I'd like to sort of reflect on Maslow's hierarchy of needs, because I think this is an interesting sort of scene setter. So Maslow, back in 1943, published his paper, A Theory of Human Motivation, which sort of outlined that essentially there were 5 human needs. And they were in some kind of hierarchy going from the bottom of physiological to the top of self-fulfillment or actualization. And he proposed that this is what people as individuals needed to sort of develop in their lives. That first of all, it was about food and water and sleep, and then it became about protection and stability, which is where work and employment kicks in, and then it was more about love and relationships, dealing with small groups, so transitioning from the individual to being part of small groups, and then self-esteem, which delivered confidence and achievement and respect, so the sort of wider group impact came in, and moving to societal type thinking, and then at the top of this hierarchy, self-fulfillment and actualization, which is fundamentally about personal growth, fulfillment, and much wider success, so an impact on a wider platform. And Maslow proposed that as each of these needs was fulfilled, individuals sought to fulfill the next need. Now, that's been debated over many years, that actually there's an overlap. These things are not discrete in the way Maslow described. However, there is this natural progression of the impact, moving from individual at the bottom of the hierarchy to societal at the top. And that's an interesting sort of thought to sort of hold in your mind, because in more recent times, a young graduate in the UK, Becky Naylor, revisited Maslow's hierarchy of needs and said, hey, with the onset of internet capability, Wi-Fi, mobile functionality, there's actually now potentially 6 needs. And I want to introduce this notion of connectivity as a new need, which comes in third up from the bottom. And in Becky's paper, it sort of introduced this concept and said also within the sort of love and belonging part, you've got social networks that spin off from connectivity. And that's really interesting, because I would argue that connectivity as a need in this has created noise and disruption within the needs hierarchy. In other words, what I'm saying is it's slowed down the transitional to societal thinking. And that's quite an important consideration, because when you look at modern behaviors of individuals, I think it sort of reinforces that we're more focused on thinking about ourselves and thinking about small groups rather than thinking on a wider plane. So I think there is some mileage in this sort of revisited notion of Maslow's hierarchy. So let's move forward to the introduction. And I'm going to open this by saying, as a society, are we short-sighted or are we far-sighted? And I think that's up for debate, and we see both sort of behaviors present all the time. But I would argue we're moving more short-sightedly in many aspects of what we do. So let's take an example. When you journey around your local or home city, what do you in fact see on a regular basis? Masses of traffic, much of it queuing, I would argue, equal masses of maintenance work, whether that's to roads, to buildings for utility purposes, etc. And also you see masses of what I call urban beige with few green spaces. And have we accepted this sort of evolution of the urban environment or the concrete jungle as a norm in our lives? And do we see urban disruptions as just part of normal everyday life? Have we, or do we not, consider the consequences of all these changes and all these events going on daily around us? And has mass urbanization, therefore, created a blind spot in our view of what is acceptable and reasonable? So I think there's a number of sort of questions that are pertinent. So I would say much of what surrounds us today may be described in 2 statements. They are features of a disposable society, and they are aspects of an install and repair structural culture. We're not thinking about longevity in the way we perhaps should. And built to last seems to be an absolute anathema in today's society. But hey, why? Built to last was always something people were proud of in the past. So have the marketing gurus got too far into our heads with their very smart approaches to making us desire things? Have fashion for products driven a personal need to constantly refresh and update, even if it's not really necessary? And have we therefore just embraced short-termism as the norm? So I would argue we have a genuine lack of urban resilience because of this install and repair structural culture, and we find it easy to throw things away rather than fix them. And we've even in more recent times given that a name. We call it recycling. Now, recycling is a nice word, it's a lovely word, and we should do lots of it. And we think we're doing lots of it. But the reality is we're probably not doing anywhere near the amount, because what happens after we take recycled products to the bin at the end of our garden or the end of our street or to a recycling centre, stuff doesn't get recycled. The metals tend to have a higher recycling rate, other materials far, far less. Plastics, only 9% recycled at a global level, which is so disappointing. So just a couple of reflections on those last slides. Is what we see here acceptable? It cannot be. I mean, it's just a pollution engine at worst, and I don't know at best what it becomes. Should this be what we see as the daily norm, this constant urban maintenance? I think I would say it's driven by an absence of resilient thinking. We don't have the right alignment. So a year ago, within World Stainless, we started looking at life cycle thinking in a bit more detail. We'd had flirtations with life cycle costing, but we started thinking about it, what I would call properly. And one of our early thoughts was, hey, this looks so obvious. Why are people not doing it? Is it a case of obviously the obvious is not obvious? Or more people would be changing how they think and how they operate? And I think this is an interesting reflection. What stops us adopting life cycle thinking? Because we do have some really gifted people across our businesses, in our academia, wherever, lots of gifted, capable people. So what prevents, I should say, businesses from making this sort of paradigm shift? Are our organizational cultures so far embedded they can't adopt, they can't shift to a different approach? Has the McDonaldization of society modified our thinking? You know, it's been around for 50 years. Are we sort of just embracing that? Do we not understand the unfolding impact of what stands before us in terms of climate change and the impact? Or have we just abandoned societal thinking, or is it some combination of all these? So I'd like to move on at this point to talk about resilience. And I think resilience can be described in 3 easy steps. We develop some insights. From those insights, we learn something, and from that learning, we develop. And when you think about resilience, it's about understanding things that have gone wrong. So have we manufactured things in the wrong way? Have we chosen the wrong materials, etc., etc.? Those are the insights. And then we learn from those insights. In this environment, we need to change these things, and then you develop. However, I believe currently resilience gets overlooked because the upfront cost impact forces learning to be dismissed, and therefore the outcome is stagnation, not developing resilient structures, systems, whatever. So do we routinely consider costs from a holistic perspective, or what I see more of, a short-sighted perspective? So let's think about resilience in a particular field, that of cities. And it's easy to define from the United Nations documents on this, that a resilient city, a truly resilient city, assesses, plans and acts and prepares for and responds to all hazards. And that can be sudden things, slow onset things, the expected and the unexpected. And we have all those things happening in our world all the time. If we build cities that are more resilient, there is no doubt we will save lives, we will save resources because they will withstand things, and the impact of interventions will be better, and we'll save the environment. So all good things. And our future, I would argue, depends on doing this. We have to do these things. And across many cities of the world, resilient city frameworks are being developed, which is great. Great to see, great to hear. And long-term planning is a cornerstone feature, whether that is for infrastructure, for connectivity, etc., etc. They all feature some bold statements on long-term planning. But what's missing virtually none of them talk about resilient materials in a very open and direct way. And that's a worry, because are we leaving the door open for old behaviours still to creep into resilient thinking? So urban resilience, I would argue, cannot be achieved without using resilient materials. The things go hand in hand, and that's really important. So let's look at an example. Barcelona is defined as a resilient city. Excuse me, it's a champion city of urban resilience, and it offers support to other cities, which is fantastic. There's no doubt that's a really interesting approach and a good step forward. For Barcelona, they have 4 primary risks. That of flooding, both flash floods and coastal floods, and that's because there's an increase in urban pervious surfaces, which has gone from 45% not many decades ago to over 70% now. So they have a problem getting rid of floodwater. They're also described as a heat island, which is the temperature difference between the urban setting, the city itself, and the surrounding rural environment, which becomes quite extreme in the hot periods. They also suffer from droughts. They are defined as a crisis-prone city, and water loss prevention is an urban priority, and that's really good to sort of see and hear. And they're at risk of the impact of forest fires. Being in the Catalonia area, it's highly prone to fire risk, and the impact strikes both the forest and the nearby urban settings. So they have a number of primary issues to deal with. So if they are to protect against all these things, you need resilient materials. There's no question. You can't debate that, because as some of these things get worse, you will struggle to sort the problems out. And resilient materials will give you this solid protection against these primary risks for many decades to come if they're used appropriately. So let's think about now how we deliver the message about resilient materials. So resilience and life cycle thinking naturally sit together. Life cycle thinking promotes resilient materials, and resilient materials themselves require much less what I call operational interventions, ranging from simple cleaning to partial and total replacement and all the maintenance requirements in the middle. Resilient materials actually support the green transition, because much fewer interventions, which is a consequence of choosing resilient materials, delivers much lower greenhouse gas emissions. And I'll illustrate this in a forthcoming slide. Resilient materials, because you don't have to intervene and replace things, helps to protect scarce resources. It either stops things leaking, like water loss, so you don't have droughts and you don't have to restrict water supply, or it withstands things very effectively, so you don't suffer from flash floods, etc. Resilient materials therefore allow us to achieve more with less. We can move away from infrastructural install and repair to the notion of fit and forget. And resilient materials are almost always sustainable materials, and that's an important marriage, that we understand that connection. So let's look, excuse me, it's a very simple material resilience table. I'm not trying to be overcomplicated here. So I've looked at 5 materials or material groups and put down there the sort of service life, life cycle costing status, life cycle emission status, and impact on co-materials where that's important. And it is in many cases. Many structures are composite structures, so co-materials are important. At the top of that list, you've got, and you wouldn't be surprised by this, nickel alloys, stainless steels. They have long service lives. There's a slight difference in life cycle costing. Stainless steels do tend to be much lower. Life cycle emissions, they're both low because they don't need the interventions. General steels will have a shorter but respectable service life with reasonable life cycle cost, but suffer on the emission side, as does aluminium. And then high density polyethylene at the bottom is not going to last terribly long. In some cases, it lasts much less than 10 years. But from a life cycle costing perspective, it's rubbish because you're constantly replacing. And from an emissions perspective, it's pretty rubbish too. You can't get away from that. But some of these materials, particularly those in the upper section of this top table, have a positive impact on the co-materials. So the perfect example is concrete. If you want to reinforce concrete, you're probably going to choose a steel of some sort. And there's differences. If you choose stainless steels with its very high strength, particularly the duplex stainless steels, you can reduce the weight of concrete. So you have another impact, a knock-on positive impact, which is really good. General steels just fall a little bit behind, but still can have a positive impact there. So this is about thinking about your materials and their impact very carefully. Glass is often used for sort of external features of structures and has some amazing effects when used appropriately, but you have to balance it because its life cycle costs and life cycle emissions are not so good compared to some of the metal groups. So it's all about matching things appropriately, but recognizing for the key materials their sort of resilience status. So there is no doubt that resilient materials offer much improved societal impact, and we shouldn't forget that. So let's move on now and think about, hey, what is life cycle thinking? So first of all, it means accounting for things from an economic, an environmental, and a social perspectives. What are the impacts on these three dimensions? But also it means thinking across all stages of a product, an installation, or a process life cycle. So we're going from birth to death, from cradle to grave. So it's end-to-end thinking. And when you start to take that perspective, it informs on the following things. So it's the impact of the process and products that are produced from an emissions perspective, from a service life perspective, from the needed level of interventions, I should say, and the impact on employment levels, which we should never forget in this because we're dealing with humans all the way along this. And also considering service life cost and emissions are critical in this, because what you want is a service life with minimal interventions, and interventions impact on cost and emissions dramatically. So it's really important that we think about those three things together. So life cycle thinking is always holistic. So let's try and illustrate that. So I'm going to illustrate it with two different material choices. But let's start by throwing a timeline in of 0 to 100 years. And this is an example of a traditional materials choice that you install the thing, build the thing, whatever. Choice 1 with traditional materials. It has a design operational life of 100 years. You do some snagging work after installation or creation just to solve a few sort of problems at the start. And then after that, over the term of the 100 years, you have regular maintenance requirements. And, this is just illustrative. So, please recognize that it's a simple illustration. And then we have the choice of the same thing made with resilient materials. So you have the same, you create the thing, you have the same snagging requirements, a few issues to start with on day one. And then you think about maintenance. And because you've chosen something that's resilient, you have far less maintenance interventions. You never quite get to the perfect fit and forget, but you get very close, and resilient materials deliver that. But this is not the whole story. This is not the only way to illustrate this. So let's just look at these two options in a little more detail, I should say. So again, we put the timeline back in, and here's the simple model for the traditional material infrastructure, piece of infrastructure or installation, option 1. And then when you think about what happens to costs or emissions, this is the sort of picture that you get. So if this is cost, you have a cost for the installation that you've created in year 0. You have some extra costs for your snagging work, solving the little early problems, and then you have costs for the maintenance that varies a little bit over time, but essentially fills that box. And and you could apply that to emissions in the same way. The emissions profile will look something very similar. But when you look at option 2, again, we throw the timeline back in. This is how option 2 looks. Well, of course, things look different because you've not got these interventions. And when you put this purple line in, which was the initial cost for option 1, and remember it filled the box, then this is a much more interesting concept. Choosing resilient material brings you so many more benefits. So let's try and describe that in a few sentences. So typically you will get a cost reduction. better than 20% is the norm. You will get an emissions reduction, and this figure may stagger people, better than 40%, because most of the emissions associated with something are in the operational phase. They're not in the material creation phase. You will get a significantly improved operational asset uptime, and that gives an opportunity to enhance profits. And you shouldn't overlook that, because that can boost other benefits for the operation of that installation, whatever it is, or product. You simplify the operational management tasks because you have less interventions, so you make life easier. You create a positive societal image, because if you've got less interventions, it's not visible in the same way, and so that will increase how the business is viewed and increase business footfall. And you completely remove the supply chain bullwhip effect, which means less stagnant inventory in the upstream supply chain that would supply materials needed for maintenance work. So another positive impact that's a bit outside the scope of the installation, product, or whatever. But there are also some considerations. So when you look at life cycle thinking in this context, you need some different societal thinking to allow the transformation. So maintenance needs for an installation will undoubtedly go down. So that means less resources are needed, including people. So it's a reduction in gainfully employed people. However, on the upside, the planning needs to create these installations will be increased, because it demands more thinking, more careful thinking, different materials. So more resources are needed. So I would argue there's a neat balance here between less resources on one hand and more resources in another area. But also, as I mentioned on the previous slide, the supply chains have to rebalance, particularly the proportions that are made to stock versus made to order. And with less inventory needed, it supports the notion of more just-in-time production, which is much better overall, because it means the inventory is moving and not stagnating. So, having set the scene, why would we adopt this approach? I mean, some of it may be fairly obvious based on what I've shown, but it is a solid method for demonstrating material sustainability, and it guides material selection decisions. It can be aligned to specific applications to make decision making much, much easier. And it can be centered around three simple sustainability themes: life cycle costs, because upfront costs are only part of the story; life cycle emissions, because material production emissions alone do not paint the whole picture by a long way; and a comparison of material attributes, the key attributes needed for the application to allow optimal material selection. So, key question, can we afford not to do this? I think the answer is no. Now let's just look at this. This was an early prototype we created just over a year ago within World Stainless. And this doesn't look at a particular application, but it looks at a series of important attributes. So we wanted an application where the material shouldn't degrade during its service life, and we're looking at 100 years here. So we want uninterrupted service life with no material degradation. The material had to be resistant to regular impacts, and we also needed high material strength. So thinking about those things, we looked at two different stainless steels, an austenitic and a duplex, a carbon steel, a high density polyethylene, and aluminium. And on year zero, on the right hand side, from an emissions perspective, the plastic product, the HDPE, looks very interesting. It's much lower, much lower than the rest. And all the rest sit in differing positions. But then as time progresses and interventions and partial replacements, maintenance are needed, things change. The only thing that doesn't change is the stainless. The stainless products just sit there and perform in an application that requires these sorts of attributes. So by the time you get to 30 years, you start to see a difference. The plastic has fallen out of favor on this assessment. By the time you get to 60 years, really only stainless is looking interesting. So when you map things out in this way, you start to gauge an idea of how resilient your materials are. And I think that's really important. So this gave us some enthusiasm for developing things further. And the important thing is we put a lot of time and effort in looking at reducing materials production emissions, and not necessarily to choosing the right materials to reduce life cycle emissions. So we need a change of focus. So let's now use a short illustration on life cycle costing, because I've just done emissions. And this is a 1990s example, the Schaffhausen Bridge, which is a bridge over the River Rhine, and it was completed in the mid-90s, in 1995. And the requirements here were the bridge had to resist atmospheric corrosion and heavy use of de-icing salts. It should last for at least 80 years without any loss of structural integrity and without significant maintenance. And the bridge itself was going to be primarily a steel and concrete structure, so a composite structure, and therefore the concrete would require some kind of steel reinforcement. So 3 reinforcement material options were considered for this bridge. Carbon steel. Choosing carbon steel would have meant that expensive repairs would be required approximately every 25 years, and the effect of that would be massive or heavy traffic disruption. Another option, epoxy coated carbon steel. Less extensive repairs, but still every 25 years. And that's because the epoxy coating would degrade and start the corrosion of the carbon steel. And that would cause some level of traffic disruption. And the third choice was using carbon steel plus stainless steel in critical areas. And without a doubt, that met the design life requirements and virtually no maintenance required as well. So it ticked both boxes there, quite interesting. But hey, what would this cost? And here's the life cycle cost chart. So what's interesting is that stainless steel requires pretty much no intervention. It doesn't degrade, it doesn't corrode in this sort of environment, even with the heavy use of de-icing salt. So the cost at the start is the cost at the end in this example. The other products have increasing costs, but when you look at the start point, the difference between the two, because this was careful selection of stainless steel for the critical areas where corrosion products would exist very quickly, there was very little difference between the initial cost. It was about 1%. So not much at all, and not a reason not to choose stainless. And this was the solution that was chosen. And you will see that after about 80 years, the stainless steel option is about 30% lower in cost compared to either of the carbon steel options. So looking at things from this perspective gives you great information and takes away a lot of headaches along the way. But how can we demonstrate material sustainability? Well, when you look at a lot of data, things that are quoted as important are service life, the ability to both reuse and recycle materials, looking at the attributes that are key for the product or the installation and the co-materials impact of those attributes, and looking at the life cycle things we've just talked about, costs and emissions. So from that, within World Stainless, we've developed a sustainability model that has a comparative material attribute assessment. It has the life cycle models covering costs and emissions, and the documentary evidence to back that all up. So how does it work? So from a life cycle cost modeling perspective, we have a cradle to grave model for competing materials, and we develop those for different applications. So a new application requires a new model. We compare the primary attributes that are needed for that application and the attributes that influence material selection decisions, plus the true recyclability of the materials we're assessing. And then we look at the life cycle emissions modeling works. That's all the major emission elements are included, whether it be production of the input materials, fabrication of those, transport, maintenance, etc., etc. Everything's included. And as I said, the models are developed for defined applications. So one application, one model. Several competing materials are assessed, and the output is compelling, I would argue, material selection guidance. So from an overview sense, the model is divided up into 3 parts, but 4 parts are shown here because within the attributes, the salmon pink element of this, recycling just to the left of that is a constant. So all the other attributes can change, but we never lose recycling because recyclability has an impact on emissions without a doubt. And the other 2 elements of life cycle emissions and life cycle costs have similar or fairly equal weights in the overall model. So I'm going to now illustrate this with an example using urban seats, and this photograph's from the city of Melbourne in Australia, where they've adopted stainless for their urban furniture for some time. And this is the life cycle cost model, and what you've got here, and in Melbourne, just to put things in context, they had a choice of two materials, galvanized carbon steel or stainless. So what I've done with this is you've got the lines for carbon steel and the line for 304L stainless made traditionally with high scrap, the red and the blue lines respectively. And I've also put on two other variants, 2101 lean duplex, the green line, another stainless product, and then 304L made through the nickel pig iron route. So a different option there. What's interesting is when you look at the cost progression over 50 years in this case, there is no doubt that the cost of carbon steel increases much faster than the cost of stainless steel. And in an urban setting, you've always got things to do. There's always cleaning tasks. There may be some replacement tasks that I'll talk about. But there is an interesting difference here in how these costs are built up. So let's look at the key elements of the life cycle cost model. So you've got the initial material cost, and stainless in this context is about 1.7 times that for the galvanized carbon steel. So hey, you can perhaps understand why people say, oh, I don't want to spend my money on stainless. It is more expensive. Yes, it is. Then you've got the processing, profit and tax for making the things. And stainless there is about 1.2 times more than that of galvanized carbon steel. And then you get the installation cost. Well, that's the same for all materials. It costs the same to install one seat made out of galvanized carbon steel as it does one from stainless. No difference. But it's about 6 to 7% of the total item cost. Then you get the cleaning cost. It's an urban setting. These things want cleaning. Pretty much the same for all materials, 4 to 5% of the total item cost per annum. And then we get to the interesting point, maintenance costs. For stainless, absolutely zero, nothing at all. But for galvanized carbon steel, it's almost 30% of the total item cost, with a repair rate every year of 15%. So quite significant. And then the last point is replacement costs. And you're thinking, hey, do we have to replace some of these things? Well, yes, you do. And it costs the same as the initial material and processing costs. And the damage rate is about 1% of all installations each year. Now, why? It's contractors. Contractors driving yellow goods, doing useful work, demolish urban street furniture. It just happens. And I guess that will always happen to some degree. But what's interesting is the big cost category is maintenance. So if you can do away with that, your life cycle cost position looks interesting for the sustainable materials. So what are the features? Resilient materials have higher upfront costs, typically 50% or more, but they offer a reduction in co-materials where they are used, and that will reduce the gap to probably 30% or a little over that. Life cycle cost parity is generally achieved somewhere between 6 and 10 years. Timescale depends on each application. And resilient materials will deliver life cycle costs some 30+% lower after 50 years when compared to non-resilient materials. So it's like, why would you not make this choice? And if you think about our personal lives, when we make large purchases, we often do that in a manner that resembles life cycle costing. So if we can do it for our personal settings, why do we not do it in business? So let's move on and do the sort of comparative reference from Melbourne. So the city of Melbourne, they started using stainless for street furniture 35 years ago, and their own life cycle cost models support our data almost perfectly. In fact, their payback is a little faster. We've got 6 to 10 years, they're saying consistently 7 years, but it's in the range. They have a resilient materials champion in their design team, so that's really good. They've got somebody with the right head on, and they have a simple philosophy. They're a city. Focus on things that are visible and make them stunning and timeless, and then you do not become a donut city. In other words, everybody lives in the suburbs and nobody comes into the centre. You bring people into the centre, you stimulate economies, you get economic growth. It's quite simple. So Melbourne is a great example of both life cycle thinking in action and the use of resilient materials, and altogether they have less interventions and they spend their money wisely. But let's go on and look at the attributes that are associated with it. And I'm not going to go through every attribute here. You can read this. But when you look at the top scoring ones, they're all aligned to the stainless product. So why would you not choose it? So even the attributes line up perfectly, and that's looking at strength, energy absorption characteristics, graffiti removal costs, hygiene factors, operational lifetime, how easy it is to fabricate, and then of course at the end, the recycled percentage. All steels are good. 96% is fairly typical. So stainless steels outshine carbon steel for this application. Well, let's move on and look at emissions, and this is really interesting. And I've added into this chart, because we had the data available, high density polyethylene and 304L stainless via the nickel pig iron route. What is really interesting is the stainless products in the middle are much, much lower than the others. And the other feature is, where are the emissions coming from? They're coming from maintenance and they're coming from replacement work. So, hey, this is where the emissions sit. And if we want to have an impact on reducing our greenhouse gas emissions, choose the materials that don't need so much of these things. And so that's a very simple message. Don't look at reducing, well, we should look at reducing the production emissions from material, but it's not where the problem is aligned. And then the final assessment shows that both 304L made with a lot of scrap and 2101 lead duplex are the best choice of materials in this option. So the conclusions here are materials that need lower levels of intervention provide the best scores in each category consistently. And if you avoid damage to your installations, you always also deliver lower life cycle emissions. And maintenance and replacement have the highest negative impact in the scoring in each category. So those are the things to avoid. Think resilient materials. So I've now got to the point where I'd just quite like to sum up where we are and hand over to questions. So I've got 3 last slides. I think we all understand we've loads of challenges to overcome to truly save our planet, but we've become engulfed by some suboptimal cultural mindsets, short-termism, the disposal or convenience society, and individualism. They're driving our behaviours in somewhat the wrong way. It's not that we're not well-meaning, we're just being dragged or driven in the wrong way. Social media, for all its benefits, is creating too much noise, so we can't see beyond the noise. We can't look up to look around, and I mean that both physically and metaphorically. Just take a look walking around a street in your local city. How many people are walking with their heads down, embedded in their mobile phone? Too many. And are we in a world where all options, all opinions rather, are all provided, and we've allowed our future almost to be pre-decided? We need to change things, not give up. And we have relatively few years to make changes before climate change makes change impossible. So we've got to change our way of looking at all aspects of our lives, because we live in a logjam world. It's inefficient, it's not good, this is not progress. So we must adopt life cycle thinking to adopt sustainable materials. And if we choose that, then things get better. Waste goes down, emissions go down, we use our money wisely, and we protect our society. And I think we owe that to the generations to come. So we should choose resilient, sustainable materials now. And of course, there is another option. We don't have to do any of these things. Survival is not mandatory. And with that, I'd like to thank everybody for their attention and say, hey, are there any questions? Joe, do we have any questions that have come in?
So far, oh wait, here's a question. Why do many people still select materials that degrade or corrode for large structures?
I think there's probably a number of reasons why that happens. One is, in organizations, people become comfortable with doing things a certain way, and they get a confidence from that. So they keep doing it. And it's almost that statement right at the start. Insanity is doing the same things over and over again and expecting different results. people are confident working with certain materials because they know what to expect. But I think also there's a separation between what happens in creating something and what happens in using something. The two aspects, which are a total part of using something effectively, are not joined up. The thinking is not joined up. So the creation of something is, the responsibility for that is aligned to group A, and the use of it is aligned to group B. And these two groups don't meet. They don't get their heads together and sort things out for the better. And I think that's something we have to change. We have this societal wall between the creation side and the usage side. And the only time we knock that wall down is when we're thinking about things for ourselves, not thinking about things on the wider plane. So I think that's fundamentally one of the issues. I think also the not invented here syndrome is alive and well. And people often don't like change. They're very suspicious of change. So when you offer something up that's quite different, there's a fear, there's a natural fear, and I get that. But we have to overcome those fears, otherwise we will not progress. So I think there's a number of things going off, but organizational structure and organizational culture are probably very much at the heart of it. Anything else, Joan?
Yeah, there's another one here. The idea of life cycle thinking is logical and straightforward, but is not yet universally adopted. Why do you believe this is the case?
Well, I think some of that parallels to some of the things I've just said, but I think also we've created, and I'll go back to the sort of McDonaldization of society, we've created this notion of single use. And along with that comes the notion of getting things very cheaply compared to how things used to be in relative terms. And when you start to adopt sort of life cycle thinking and more societal thinking, you have to accept that the upfront costs are going to be higher, but the operational costs are going to be much lower, and overall you will win. But we haven't yet engineered the solution where business is won on the basis of resilience and sustainability. It's still won on the basis of cost. And that is a paradigm shift that needs to be adopted quickly. That we take away this upfront thinking, this short-term thinking, and get our heads around life cycle thinking, because there are finance houses out there that will support this thinking. They want to work with people who are thinking in this way. So the ability to do this thing is not sort of restricted. We just have to think differently and move away from something that's become embedded for many years.
There's another one here, Tim.
Yeah.
How carbon credits from recyclability of steel are allocated in the cradle to grave steel sheet LCA. Is there any certificate mechanism to avoid double counting since there is a system boundaries issue?
Yeah, and that's a really good question, because I have a real sort of dilemma with carbon credits. So if something is put into an installation, and let's just pick a number, that it has a CO2 production emissions of 2 tons of CO2 per ton of material. It's a very simple case. And if that is recycled, let's just assume the credit is 1 ton of CO2 per ton of material. So keeping the numbers really, really simple. I'm not saying this is accurate. However, when you come to replace the material and take it out for recycling, I think the fundamental question is, when are you going to recycle that material? Because the recycling of it is the birth of another product. So what you don't want is this double counting thing. Excuse me, because when you create a new product in what I call a second life, you get a lower emissions profile by using recycled material. So if you were to give a credit back to the original material, which on one method of assessment is actually done, you can't count it then in the birth of the new material. And I think that muddies the water. So I think what you have to do is say, when I go to recycle something, which is great and admirable, the benefit of not having to dig raw materials out of the ground, out of the earth, gives me a lower input emissions benefit, because I have to do less work to create this raw material, the scope 3 emissions, and therefore I should take that in the next life, not grab part of it at the end of the life of a particular material. And all that does, if you adopt that approach, is reinforce using sustainable materials. I hope I made that clear, but it is this double counting thing. You can't have the benefit of a recycling credit in the life of item or product 1 and then have it again at the birth of item or product 2. I think you can only count once, and I think the end of a life, that credit should go into the next life. I hope that makes sense. But in terms of a standard, hey, there's lots of people approaching this different ways, and I think we are potentially at risk of greenwashing if we don't make things really clear here and avoid this double counting. Because if we are to keep the sustainable bandwagon, so to speak, and the resilient materials bandwagon rolling, everything needs to be treated in discrete elements. You create something, it comes to the end of its life. You create a new thing, and that comes to the end of its life. And everything's compartmentalized in that way. And I think then you can define the boundaries really clearly and not double count. So I hope I answered that question.
Yes, there's a thank you coming, so I think you must have answered that question. So I don't see any new questions coming in.
Okay. But of course, you know, if somebody wishes to contact us with a more detailed question after they've thought about this and maybe reviewed the presentation, we're more than happy to do that. And because we've got a few more minutes, I didn't mention at the start, there's a handful of appendix slides with this presentation. And one of them is really interesting. It's focusing on stainless steel reusable drinks containers, which I guess most people have seen. And I don't necessarily want to dwell on, you know, this direct promotion of them. What I'd like to dwell on is this stuff, that a stainless steel bottle, we've been using them time and time again, and we've now got over 1,000 uses of a single bottle, and it still works perfectly. Costs about 30 euros, and the emissions associated with that are about 543 grams of CO2 to produce one water bottle. Compare that to a single-use plastic bottle that costs virtually nothing, you know, 25 euro cents to make, and 80 grams of CO2 emitted producing one, you know, complete difference. But when you think about replenishing the use of single-use bottles, then the cost stacks up. It becomes much bigger than the 30 euros that you spend on a stainless water bottle, and the emissions jump up massively. So you're talking, you know, 53 kilograms of emissions compared to the stainless of half a kilogram. So huge difference. And I think we need to reflect on that. And the other thing is water supply. Tap water is 4 process steps, essentially 0.35 grams of CO2 per litre of water, not much at all. Bottled water, 10 process steps, 203 essentially grams of CO2 per litre of water. It's like, are we mad to adopt bottled water? You're just naturally polluting. And buying 2 500 milliliter plastic bottles of water every week throughout a year adds more than 10 kilograms of CO2 to our atmosphere. This is a no-brainer. Let's, you know, get the right bottles, fill them with tap water ourselves, and avoid creating CO2. The power of this is in our hands. We don't even have to make major changes. So I just wanted to reflect on that whilst it was in the appendices.
Well, nothing further has come in, Tim, and
Okay.
although we still have a few minutes, I think we can wrap up here.
I guess we can. I'd like to thank everybody for their attention. Thank you for attending. It's very much appreciated. Thanks for the questions. And I wish everybody, if you're celebrating Christmas, have a lovely Christmas. And I hope whatever you celebrate towards the end of the year is also successful. And hopefully we see you at one of our webinars next year. Thank you very much. Take care and goodbye.